Okay, everyone, welcome back. I'm chairing this afternoon's session, and we're going to start out with some comments by Peter Landweber in remembrance of Fred.
Okay, I have an opportunity to tell you some things about Fred Cohen, and it's a pleasure. Uh, well, I've known him for many years, but not very well at first, because we didn't have common interests. He wasn't too interested in cobordism theory, I think. But I certainly knew about him, knew his reputation. Uh, then recently, not too many years ago, he spent a year at the Institute in Princeton, and that was a revelation. What a wonderful fellow Fred was, uh, in my memories. So that made that an enjoyable year for me. He was generous to the extreme, as I will tell you a little the bit incident, a more recent incident that we shared. Uh, Also, once went to his office up, I think, on the fourth floor at the Institute with a question, and I found he seemed to be essentially holding office hours. That he was advising various people, also someone, I forget his name, but someone Fred knew well was sharing a portion of the office with him. So there was a lot of talk, and it was very interesting. And when it became my turn to ask Fred a question, well, I thought it was less interesting than what he was talking about, and he said, "Yes, it should work out, no problem." But that was my office hours experience with Fred. Uh, as a journal editor, I think Fred was a remarkable person. Uh, well, what am I about to say? Well, he was very generous and fair minded. And okay, he asked me to referee a paper for his journal. And I even forget the name of the journal. Uh, so I did referee it. But I'd mentioned that I didn't really want to say should it be the paper should be accepted or not. I just wanted to look at the paper and give him my thoughts. So, all right, I did it. Had a little exchange with the author, who I'm not mentioning, and then I noticed though it was a sort of offbeat topic, even though there wasn't one nice argument that I called attention to. And then the paper was revised after taking into account a few suggestions that I made, and then Fred asked, did I recommend that it be accepted? And I reminded him that I'd said I didn't really intend to answer that question. It was up to him. It was up to Fred to decide what to do. And after a little chatter about that, uh, he agreed he would take it upon himself to take my opinions into account and decide whether to accept the paper. Well, after a little thought, and he got back to me and said, yes, he has accepted the paper. And I thought that was a wise decision. And I was glad that he sort of understood where I was coming from in asking that decision to be up to him. I also knew that Fred was rather helpful to a Rutgers colleague, Abbas Bari, that's as opposed to Tony Bari. Note the different pronunciation, Bari. But he was an outstanding mathematician, and Fred served as sort of a consulting topologist for Abbas, who had wide interests that were not very specialized toward topology. Well, I think you will probably have found that Tony knows many more interesting tales about Fred, and I hope he will tell you some and that you will enjoy them. So that's all I can say. I'm delighted to have this chance to mention some things about Fred. Thank you.
There we go. That was nice. So before we get started with our first talk, Paul's going to tell us a fun little story.
So I've been asked to repeat the story that I told on July 7th, I guess, welcoming everybody to Toronto in the first workshop, but a lot of you weren't here for the first workshop, so I'll replay the story. So this is a story of a walk with Fred, and I need the stick to point things out. The Fred stick, right? This is a replacement for the Fred stick. So this is a story of a walk that I had with Fred. We met somewhere around here, and we start and go for a walk. We get to around here. Well, we get to pretty close to there. And Fred is going along talking as he often speaks. And if you know the way Fred talks, there are pauses in his speech. So Fred is saying, well, suppose you have a group. And some guy on the street that I've never seen before says, well, just any old group? I mean, don't you have any hypotheses? So anyway, so Fred stops and talks to the guy for half an hour, as is custom, as Fred's custom. Turns out the guy is a graduate student in computer science. Like if he'd been in math department, I probably would have seen him, but I never saw him before. So after about half an hour, the guy departs, heads off towards the subway, and Fred and I continue along, and we take the turn here, and we get to somewhere around here, and we see the following. If I can bring this up. Supposed to do something with this. Oh, I'm supposed to press over here. Okay. Alt something. Oh, we see this. They had to get in front of us, right? Now, I understand this was in the late 1990s when a lot of people considered the ARF invariant problem as the major unsolved problem in math, right? Certainly, there were a lot of people like Mahawold who were working seriously on it. And it might be interesting if you can read the small print, you might see what ARF stands for. ARF. So this was very appropriately named, shall we say. And anyway, I guess that was their story. So this building is very close to here. And in fact, if you go out on the balcony, you can actually see the back door of that building, but this sign is on the front, so you can't see anything. I mean, you can see the back of the building if you go out there on the balcony, but the front of the building as it was then, right? This is a picture as it was then. If you go to that now, the ARF, you can see the remains of it, but it has been sandblasted off the building. So if you go there, see, it's now been solved. Yeah, it's sandblasted off the building, right? It's not there anymore. The remainder is that the university has purchased this building a few years ago, and the math department is actually going to be acquiring space in this building, and a lot of the graduate student offices will be there. Anyway, okay, that's the end of my story. I have this color version if anyone wants to. This is my own copy that I took myself, and I actually made a copy of this, and I sent the other copy to Mark Mahowald of this picture. Anyway.
Okay, thank you. I think we'll get it set up for our first speaker today is Karen Vogtmann, and she's going to tell us about grafts, surfaces, and handle bodies. It's just need a second here to get.
All right. Oh, yes, I'm sorry. Yeah. Share screen. Okay, right. And I still want to share screen. Screen. Start broadcast.
No.
Can't. Ta-da. Okay, great. Okay, well, as everybody else, I'd like to thank the organizers for organizing this and for inviting me. And as everybody else, I should probably tell stories about Fred. I actually didn't know him all that well. I was at Cornell for 25 years, and we have this Cornell Topology Festival, which some of you may have heard of or been to. And he often came down from Rochester. And so I would talk to him. Well, that's not quite right. He would talk to me. And he said a lot of interest. He was interested in automorphisms of free groups, which is something that interests me. But we never worked together. As I said, he just told me stuff, talked to me. But actually, the first time I met him was in 1989. So this is a photograph, which is proof of the fact that Fred liked to hang out with geometric group theorists. So this is a 1989 conference at MSRI in Jim. Well, yeah, I'll get to you, Mike. But that's Fred in the middle of a bunch of geometric group theorists and other interesting people. As far in this picture, you might also recognize this guy. That's Mike. You get to see him talk tomorrow. Or this young woman. That's Ruth. Yeah. That's me. Well, that would take the hour. But anyway, those are the only 4 people in this. Frank Peterson? No. That's Jacques Tietz. This one? That's Jacques Tietz. No, Frank wasn't there. Okay, so those are the only people at whoops. So at this conference, there's a couple of other people I want to point out. This is Mark Culler, who's a co-author of mine that I'm going to talk about in a minute, and this is Peter Shalen. So just remember those names. Okay, so at this conference, I gave a talk. This is a lecture at MSRI about a certain space that I called XN. So this is a contractible space on which the group out of Fn acts properly. So the quotient is a rational model for B out. So the reason I circled Mark Culler on the last slide is that this was joint work with Mark, constructing the space and proving it was contractible. And I was talking, so that paper came out in 1986. This is 1989. I was still thinking about this space. And guess what? You're going to hear more about this space. I've been thinking about this space off and on for 40 years. So, But, and why did I circle Peter Shalin? Because in this talk, in this conference, I was talking about this space XN, and Peter called out, you should call it outer space. And guess what? So it's XN is now called outer space. And because Mark and I wrote the original paper, usually in the literature these days, it's called CVN. So it now has a name. So what I want to do today is, as I said, I've been thinking about this space off and on for 40 years, but I want to show you something new I discovered about this space, and various relatives of this space. Okay, so first, I realize that not everybody here spends all their time with outer space. And so I'm going to remind people what it is. As I said, I've been doing this for 30 years, so you probably, if you've been around any amount of time, you've probably seen me talk about this, but I don't expect you to remember what I say. Anyway, here's a picture. So what is it? Looks here like a simplicial complex with all the simplices decorated with graphs. The reason it's decorated with graphs is because the fundamental group of a graph is a free group, and we're talking about, I want something on which the outer automorphism group of a free group acts. So let me describe it in a little more detail. As you can see, it's a union of open simplices. So what are these simplices? You get one for every pair consisting of a graph and a homotopy equivalence. So, right, my graph has to be connected and all its vertices have to have valence at least 3. And H is a homotopy equivalence. And it's a homotopy equivalence to an n-petaled rose whose fundamental group we're going to canonically identify with a free group. And this only works if the genus is at least 2. Yeah. I'll explain later. So all of my life, I've been calling this CVN. In this lecture, it's called CVG. And I'll explain why later. So for example, if R in rank 2, R2 is the rose with 2 petals, and I need a graph. So here's a graph, and I need a homotopy equivalence. So how do I draw a homotopy equivalence? Well, this loop has to go around somewhere. This loop has to do something over here, which spells out a word. So I'll just label that loop by that word, and I'll label this loop by that word. And so this picture right here describes this point. It's a graph and a homotopy equivalence. I also want to do that. There are other graphs that are homotopy equivalent to the rose, like this one. So in order to specify, to draw a nice picture of a homotopy equivalence here, what am I going to do? I'll pick a maximal tree in this graph and then label the rest of the edges. Okay, so here, let's say I pick this maximal tree. Supposing my homotopy equivalence sends, we'll make it simple. The blue roof is going to go around, the blue loop is going to be X. The other blue loop is going to be Y. Y. So I label this edge X and this edge Y. Okay, so there's a picture of my point. It's a graph and a homotopy equivalence. However, I picked that maximal tree. I could just as well have picked a different maximal tree if I had picked, if I had picked this maximal tree, then what loops do I have? What do I label my loops? Well, this one's still Y, but this one is XY. I've just drawn a different picture of exactly the same homotopy equivalence. And I could have picked, there's a third maximal tree, in which case I get, I get X and XY. So these are all three different pictures of the same point in outer space. So, right, so that's a graph and a homotopy equivalence. And then I said I'm supposed to get an open simplex. So I just take an open simplex with one vertex for each edge of the graph. And another way to describe this is if I have a point in outer space, that's a point in this simplex. So the point in this simplex has barycentric coordinates, which you can think of as putting lengths on the edges of the graph. So you can think of the graph as a metric object with lengths on its edges, which is the way I guess I usually describe it. Okay, and so when are two of these simplices the same? Well, it's the same if there's a graph automorphism that homotopy commutes with the homotopy equivalences H, which are called markings. So for instance, this guy, there's a obvious, if I just flip the y edge, I get from that to that. That's an automorphism of the graph, and it commutes with the marking. So in fact, the simplex corresponding to this is the same as the simplex corresponding to that. Whoops. So in fact, these aren't two separate simplices. Well, they are two separate simplices, but they're joined by an edge at the edge. I don't need both of these. Okay, so that's how the whole space is made up of those simplices, and some of the simplices coincide. You should notice in this picture that some faces of this simplex are missing. If I take this graph XY, so the going to the top up there corresponds to letting one of the loops shrink to 0. So if I shrink to 0, I change the fundamental group. So that face is missing. In fact, all the vertices are missing in these two pictures. Right, so that's the space. Some of its faces are missing, and an automorphism of the free group, an outer automorphism, just acts by changing the marking. It doesn't change the graph. So for instance, the automorphism sending y to y inverse takes that simplex to that simplex and fixes the center. Okay. So there's a picture again. It's a union of open simplices. A lot of the faces are missing. All of the vertices are missing. And in this simplex, well, I can't shrink either loop to 0. So in fact, that whole edge is missing, and that whole edge is missing. So it's just the open thing. Okay, so yeah. This is the space I described in the lecture that Fred went to, and he came up afterwards and wanted to know all about it, which was nice. Right, but so that's outer space, the classical outer space. So it's not a simplicial complex, but I actually want a simplicial complex. So what I can do is just take a union of closed simplices instead of open simplices, glued together in the same way, or the natural way. If two faces are glued, if two open faces are glued, I identify the closed faces as well. So that's called the simplicial completion of outer space. And if you look at the difference, whoops, oh yeah, the difference between the stuff you added forms a subcomplex. Basically, once you've shrunk a loop, if you shrink anything else, you've still shrunk the loop. So you stay in the boundary. So it's a little bit challenging to describe what the points are that you've added to this complex in this picture. So what I described is, let's see, I shrunk. Let's see, I'm going to shrink the x edge to 0. So that corresponds to that red point up there. Give this 0 length. But that's the same point as shrinking that subgraph of that to 0. And it's the same point as shrinking that subgraph of that to the 0 or that. So I'm shrinking the loop labeled x to 0. Those are all those pictures are pictures of that point up there. So a point on the boundary, what is it? It's a marked graph where I've shrunk some edges to 0, and the subgraph that I've shrunk to 0 has to contain a loop. Then I'm at infinity. And there are several ways to describe this point. I start with any marked graph that has this point in its simplex, and I have and I label the edges that are 0 length, and I define an equivalence relation by saying that two of them are equivalent if I can get from one red subgraph to the other by expanding or by collapsing an edge. So I can get from that one to that one by collapsing a red edge. So I can get to all these by collapsing edges, and so they're all equivalent. Same point at outer space in the simplicial closure. Okay, so the quotient by the group out of Fn, as I said, this is a rational k pi 1 for out of Fg. I can't say out of Fg, I'm sorry. It's out of Fg. So this is called the moduli space of genus G graphs. So if you look at, well, where was it? One of these simplices, if you look modulo the action of out of Fn, well, the stabilizer of one of those simplices is the group of automorphisms of the graph. And so this group of automorphisms has 12 elements. There's a subgroup of order 2 that doesn't do anything, but what I want to say is when you take the quotient, you only get 1/6 of that simplex. And when you take the quotient of a simplex that looks like that's associated to that graph, you only get half of the simplex. So I'm going to get one piece like this and one piece like this, and they glue together to give that. So that's the moduli space of genus G graphs. If I add the blue stuff, it's the moduli space of genus G stable graphs. We're going to call those stable graphs. So notice that in this picture, the marking has completely disappeared. Why is that? It's because the out of Fn acts by changing the marking. If I take the quotient by out of Fn, there's no more marking. Okay. So that's the moduli space of graphs and the moduli contained in the moduli space of stable graphs. And everything I've said works for graphs that have leaves. So your standard model graph is just going to be a rows with n labeled leaves attached at the base point. And a point is going to be a graph. And a homotopy equivalence, I guess I made my homotopy equivalences go the other way, but this is a homotopy theory conference, so you guys shouldn't care. So in this picture, the edges are going to have lengths, but the leaves don't. And then the group out of Fg is the pi naught of homotopy equivalences of my rows. So now I'm going to define a group AGN as pi naught of homotopy equivalences of that guy that have to fix the leaves. And that acts on the space, and I get a space like CDN and a space, a simplicial completion CGN. So all that works for graphs with leaves. Right. So now I'm going to switch gears slightly a little bit and talk, instead of moduli spaces of graphs, I'm going to talk about moduli of surfaces. So I'm talking always about a closed orientable surface of genus G with n labeled points. So there's a picture of one of genus 3 with 4 labeled points. And this MGN is a classical space, the moduli space of, well, it depends on what field you're in, what it's a moduli space of. If you're a geometric group theorist or a low dimensional topologist, you think of this as the moduli space of hyperbolic metrics on the surface. I've arranged 2G plus n is at least 3, so there is a hyperbolic metric. Or if you're a complex analyst, it's the moduli space of complex structures on S. In other words, the moduli space of Riemann surfaces. And if you're an algebraic geometer, it's the moduli space of algebraic curves of genus G with n labeled points. So the story I'm going to tell you today arose from conversations with a couple of algebraic geometers. So this is what they think of. Now, if you're not an algebraic geometer, well, even if you are these days, instead of the moduli space, you think of this cover of the moduli space known as Teichmüller space. And of course, if you're a hyperbolic geometer, then you're definitely interested in Teichmüller space. So the difference between the moduli space and the Teichmüller space is instead of just talking about Riemann surfaces or metrics, you're talking about the space of marked metrics or marked Riemann surfaces. So a marking here is going to be a homeomorphism up to isotopy. And then the mapping class group of S, that's the set of homeomorphisms of S up to isotopy. So that acts on this again by just changing the marking. Right. So the quotient, well, so what it facts about Teichmüller space, it's contractible. The action's proper with quotient MGN. So MGN is a rational K-pi1 for the mapping class group, which Ulrike talked about a couple of days ago. So it's a rational K-pi1 for the mapping class group. So that's pretty much why algebraic topologists are interested in it. It's a classifying space for that group. But algebraic geometers aren't happy with that for several reasons. First of all, they're interested in this as a classifying space for families of algebraic curves. And in a family of algebraic curves, you're also interested in what happens when the curves degenerate. And another reason they're unhappy is because MGN is this open, it's not compact. And they like their spaces to be projective varieties, which are, of course, compact. So Deline and Mumford studied this, remedied this situation. As I said, they weren't interested much in Teichmüller space at the time, but just they thought about the moduli space of surfaces, and they defined a compactification of the moduli space of algebraic curves, and where they allowed the curves to degenerate and develop nodal singularities. So to an algebraic geometer, how does a curve develop nodal singularities? Well, it starts like that, and it goes like that. So this is a set of solutions to some equation. You let some parameter go to 0, and it looks like that. Well, I'm not an algebraic geometer. I'm a topologist. So this is what a nodal curve looks like to me. And I start off with a surface. I'm going to allow some degeneration, and the curve is going to develop a singularity at this point. So, right. So this is my picture of this, and this is my picture of that. So if you do this, you can look at a dual graph to this situation, where to get a dual graph, you put a vertex for every component of the singular variety, and you put an edge between two components if they're connected by a node. And then we have some marked points here, so you put some leaves. And that's the dual graph in this picture. Over here, the dual graph looks like, well, there's only one component. So that's only one vertex. And there's one edge. So, whoops, it's supposed to be red. So that's what the dual graph looks like. It's got all the marked points, all the labeled points are here. And then there's this one. There's two components, two edges, and 4 leaves. Is that right? Yeah. Okay. So it turns out that this Deligne-Mumford compactification, what you were adding is it's stratified. And the stratified, there's one, the strata, there's one stratum for every dual graph you can get. And right. So what you've added to the moduli space is a union of boundary strata, and the strata correspond to dual graphs. That's what I just said. And they often make a boundary complex, which has a vertex for each stratum and an edge when one stratum is contained in the closure of another. So in my picture over here, this stratum, let's see, one of these strata, this stratum is actually contained in the closure. I'm going to get it wrong. Yeah, they're supposed to be like that. Right. This stratum is contained in the closure of that one. This one's in, yeah, this one of them's, yeah, anyway. That's a boundary complex. And you can see back from this picture that the boundary complex can be identified with the complex of curves on the surface, if you're familiar with the curve complex. So I'm going to do this in more detail for a genus, for a punctured projective space, or a P1 with n labeled points. So there's a point in the boundary is in one of 3 strata. It's either in that one of that type, one of that type, one of that type, because no matter what simple closed curve you choose, it separates 2 points from 2 other points. And so that's the only way you can do it. So the strata in this picture, whoops, correspond to this goes off to infinity, and this. And yeah, the whole thing has those 3 strata plus the center point. So you might recognize this if you're familiar with metric trees. It's a space of trees with n labeled leaves. In this case, there's 4 labeled leaves, labeled 1, 2, 3, and 4. And the boundary complex, so the center point corresponds to a 4 punctured sphere. Oh, sorry, 4 punctured sphere. With for which nothing has been contracted. So the dual graph is just that. So if you forget the center point, you have these 3 strata, and the boundary complex doesn't consider the whole space, just the 3 strata at infinity. That's really, there's only 3 of them, and they're disjoint. So the boundary complex is 3 points, which you can think of as these 3 red points in my picture, and that's often called the link of yeah, boundary complex is the link of the tree space. Okay. Now, so that's a picture, easy picture. in general, it's true that you can write down equations, and M0n is actually a smooth closed subvariety of C star. C star to the something. N, maybe? Anyway, so you can write down some polynomials, and the zero set is this M0n. And when you have a set of polynomials, you can tropicalize them. This is something that kind of codifies taking a logarithmic limit of subvarieties. And so what do? You just concretely, you take your polynomials, you change all the multiplications to sums, and you change all the sums to mins or maxes, depending on your preference. And so when you take this guy and you tropicalize it, guess what? You get the space of metric trees with n-labeled leaves. So Speyer and Sturmfels did this, and that's what they got. Yeah, so that's the space we just saw, right? Corresponds to the cone on the boundary complex. So if G is bigger than 0, then M0n is not smooth. So you can't just write down equations and do this, but you can fudge. And let's see, I think this was done maybe first by Michalkin. Defined a notion of tropicalization, which took the moduli space of genus G curves with n labeled points to a tropical version, which he identified with the space of stable metric graphs with n labeled leaves. And the vertices are weighted, and the sum by positive integers, and the sum of the weights and the genus is equal to G. So you just saw this in great detail. This is what did I call it? The link. The moduli space of graphs of genus G n. It's the same thing as we took this outer space thing. We took the quotient by out of Fn. We got this space of graphs. They're stable graphs. Maybe I should go back and show you the picture again. There we go. There it is. And so all we're going to do, the only difference to this is we're going to, at each of these points, we have vertices, we have some graph that we shrunk, and we're going to put the genus of the graph we shrunk, whoops, on, yeah, I guess I did this down here. We're going to put the genus of the graph we shrunk as a label on some of the vertices. So this picture here, this is a picture of if you take the cone on this, you get the tropicalization of M02. Okay, let's go back to where we were. Yeah.
Sounds like a big deal.
Yeah, I think so. Yeah, no, they like this. Yeah, this is not my stuff. I mean, well, except that, yeah, some of it's my stuff. Yeah. So there's well, as I said, the mapping class groups. So let me just yeah. So I've told you all about this picture and what happens when you tropicalize down here. So Beers, who was not an algebraic geometer, but a complex analyst, he was, of course, interested in Teichmüller space. So what he did is point out you can do exactly the same thing thinking of Riemann surfaces instead of algebraic curves, where so here we added pinched curves. Up here, we're also going to add pinched curves, but we're going to think of them as pinched Riemann surfaces, and we're going to add a marking. And you can do this. Bears did this in the 1970s. It's called augmented Teichmüller, 1980s maybe, augmented Teichmüller space. And you can do exactly the same sort of a thing and take the quotient, the modular, the mapping class group still acts on this augmented Teichmüller space, and the quotient is the Deligne-Mumford compactification. And not only that, but if you make a poset out of the boundary strata, then the realization of that poset is the curve complex. So my picture, this is what I've explained to you so far. You got MGN sitting inside of MGN bar. When you tropicalize, you get this cone on MGGN star. In Teichmüller space, you go to augmented Teichmüller space and you tropicalize and you get the cone on the curve complex. So you could think of the cone on the curve complex as the tropicalization of Teichmüller space. So this is a complex manifold. This is a complex orbifold. And then we come to an observation of Chan, Galatius, and Payne that notice that this link, the curve complex modulo the mapping class group, is exactly the same as the link of MGN trop. And it's also the same thing as the simplicial completion of outer space modulo out of Fn, or if you've got punctures, you have AGN. So these three people, Rohini Ramadas, Rod Silversmith, and Rebecca Winarski, asked me whether the cone on CVGN star is a tropicalization of something or other. So we have the curve complex, the cone on the curve complex is the tropicalization of Teichmüller space. The cone on the moduli space of graphs is the tropicalization of the moduli space of surfaces. So what's CVGN star the tropicalization of? Is there something? Is there some nice complex manifold with that you can add stuff to get a boundary stratified situation whose boundary complex is equal to CVGN star? And the answer is yes. And the idea is to use Handlebodies. So yeah, what I just explained to you is the outside square in this picture. If you go modulo the mapping class group over here, you get MGN. If you go modulo the mapping class group over here, you get moduli space of graphs. And what I'm looking for is something I can tropicalize to get the simplicial closure of outer space. So there it is. So that's what I need to tropicalize. So I need to explain what that is now. So it's really very simple. You've got surfaces, you've got handlebodies. Those are just basically fat graphs. So, but a handlebody has not only a fat graph, it's got a surface. So let's do that all together and talk about complex handlebodies. When do I stop? Half past, okay. So what's a complex handlebody? Well, all I'm going to do is take my handlebody and put a complex structure on its boundary. So that's what up to isotopy. So I'd have a homeomorphism from a Riemann surface to the boundary of my handlebody, and that's up to isotopy. And then I'm going to make a space of marked objects like that by just taking a marking is going to be a homeomorphism from the handlebody to some standard handlebody. So this is the same sort of a picture we've seen before. And the lemma is, the first lemma is that if you look at the space of marked complex handlebodies, that's in bijection with the space of marked surfaces. In other words, normal Teichmüller space. And why is that? Well, a marking of Teichmüller space is well defined up to isotopy. So if you have a handle body and you have a marking that's isotopic, two markings that are isotopic, well, let's just take one that's isotopic to the identity on the surface, you can just extend that to an isotopy of the entire handle body. Just by, do the isotopy of the surface, push it in a little bit, and then you've got the identity, and then you can extend by the identity. So these are the same space, the space of marked handle bodies and the space of Teichmüller space. So now we want to take this space and talk about and do an augmented version, talk about stable marked handle bodies. So what did we do for surfaces? We looked at nodal surfaces where you could pinch some curves. Well, here I don't just have a surface, I've got a handle body inside my surface. So the only thing I'm going to allow myself to pinch are curves that bound discs in the handle body. Okay, so that'll just give me some strata. And so that's what I'm going to do. That's going to be my augmented Teichmüller space of handle bodies. And yeah, so I get my Teichmüller space is contained in this augmented space. Teichmüller space is in bijection with the Teichmüller space of the surface. And the augmented Teichmüller space is a subspace of the augmented Teichmüller, of Beers's augmented Teichmüller space. And when I tropicalize, I'm going to get a cone on the boundary complex, but what's the boundary complex now? Instead, I can't just use any curve. I can only use meridian curves. So instead of the curve complex, I'm going to get the disk complex. So the tropical version of this is the cone on the disk complex instead of the cone on the curve complex. Okay, so that was the Teichmüller space of complex handle bodies, but that wasn't the space I was going to try. So when I tropicalized that, I got the disk complex. I want something that when I tropicalize it, I get the simplicial closure of outer space. So instead of looking at the markings by homeomorphisms of the handle body, I'm just going to look at markings by homotopy equivalences. So yeah, so my marking is going to be a homotopy equivalence from my model handle body to Y. And yeah, so there's an obvious map from the marked handle bodies to the homotopy marked handle bodies, which takes, a map to its homotopy class. And that extends to a map of, then I can also think about pinching boundary curves and get stable homotopy marked handle bodies. And so I get a map like that. Right, so it's time. I've been telling you a lot of constructions. It's time for an actual theorem. I should say this is by Rohini, by those four people I mentioned, Ramadas, Silversmith, Lenarski. Oh, I'm not last. Yeah, okay. So it turns out that this space is actually a complex manifold, which is interesting because if you just use, if you don't do the homotopy version, if you do the homeomorphism version, what you get is not a complex manifold because there are points on the boundary that don't have any neighborhood homeomorphic to, something in the complex plane, piece of the complex plane. However, you can prove that this thing actually is a complex manifold. And then this is the identification I was talking about. if you take what you added and subtract what was inside, that's stratified by complex submanifolds with simple normal crossings, which just means that if you look locally, it looks like the boundary inside of the manifold looks like a union of coordinate planes. So it's the same sort of a definition as if you actually had a algebraic variety, but you don't have a complex manifold. And the boundary complex is what we wanted, CVGN star. Not only that, but if you look at this map from the Teichmüller space of the Handlebody to the homotopy Teichmüller space, the twist subgroup, which does twists on the Handlebody in the disks, you know, it's just like a Dane twist on the surface. You cut the Handlebody open along the disk, twist it and glue it back together. The subgroup generated by those acts trivially on this. And in fact, the quotient of this space by the twist subgroup is actually isomorphic to this guy. So that requires some work, but it's true. And I've got another diagram. Homotopy theorists like diagrams, right? Maybe better than pictures. So it's clear that this twist subgroup is in the kernel of the map from the mapping class group to the homotopy mapping class group. If you do one of these twists, you're not going to do anything to the fundamental group. It's just going to be act trivially on the homotopy groups of your Handlebody. So it's clear that it's in the kernel, but in fact, it turns out it's actually equal to the kernel. So we've proved, I need Fred's stick. We've proved that modding by the twist subgroup is the homotopy, the Teichmüller's, by the twist subgroup gives you the homotopy Teichmüller space. Modding by the whole mapping class group of the Handlebody gives you the moduli space of complex Handlebodies. And if you restrict to the boundary, you get to the moduli space of surfaces. If you tropicalize the moduli space of surfaces, you get the link of MGN trop. Turns out, kind of amazingly, if you tropicalize, even though this is an infinite to one map here, if you tropicalize, you get the same thing. So these are actually the same. And on the tropical side over here, we showed that when you tropicalize, you get the cone on the disk complex. And we proved, in fact, part of the theorem too, which I haven't got to, that the quotient of the disk complex by the twist subgroup of the disk complex is the simplicial closure of outer space. And then if you go by, so that's, yeah. If you go further in this, so if you mod out by this, you get the simplicial closure of outer space. Then if you mod out by AGN, you get to the link of MGN trop again. So it all fits into a very nice picture, which was that giant diagram that I showed you at the beginning. So that's all a pretty, I haven't shown you any of the proofs, but it kind of involves a mixture of like Fenchel-Nielsen coordinates on Teichmüller space and some combinatorial topology. But anyway, I haven't got time for that. But it turns out that there's actually a complex analysts were actually thinking about this space, not in these terms, but in a completely different way. It turns out that our space HT V of G can be identified if there's no punctures, if there's no marked labeled points. This space TG of V can be identified with Schottky space. So yeah, I'm out of time. Okay. Well, okay. So I'll tell you what a Schottky group is in a minute. So Schottky space is a space that parameterizes Schottky groups, which are certain free subgroups of PSL2C generated by pairs of loxodromic elements, if you know what that means. And these guys, Gerritz and Herrlich in the 1990s defined a version of Schottky space, which they called extended Schottky space. And that corresponds exactly to our homotopy, extended homotopy Teichmuller space of a Handlebody. And so that was kind of neat. We were worried at first that this meant that everything we'd done was irrelevant because somebody had done it before. But we don't see any way of putting labeled points in the picture, in their picture. And also it takes a little work to understand why they're the same space. But since they are the same space, it means I can end with a cool picture of, well, I'll tell you what a Schottky group is first, I think. Yeah. What's a Schottky group? So you take two loxodromic elements of PSL2C. Those are two 2x2 complex matrices. And you want them to generate a free group of rank 2. And the way you think of it is that there's two circles in the complex plane. Infinite, you also think of infinity as being there, but the circles are circles in the complex plane. And your first loxodromic element takes the outside of one circle to the inside of the other circle. And so there's two of those. And it turns out that the exterior of those four circles is a fundamental domain for the action of this free group on the complex plane unit infinity. So the quotient by the action is the exterior of those four circles in the complex plane modulo the action of the surface of this. It's a fundamental domain. So and the red circles get identified, the black circles get identified. So what you get is a four-punctured sphere with two circles identified, so you get a surface. And the fact that you've got PSL2C means that these elements extend to the hyperbolic 3 space. So you have a little hyperbolic plane with a boundary circle on the boundary CU at infinity. And the loxodromic elements take, the outside of this guy, say, into the inside of that guy, outside of this guy into the inside of this guy. So the outside becomes a hyperbolic. After you glue them together, what you get is a hyperbolic metric on a handlebody. And of course, since these are complex, these are Mobius transformations, they glue together to give you a whole complex structure on the surface. So you get a handlebody with a complex structure out of a Schottky group. Right, so this is another picture of what happens in a Schottky group. The outside of A gets mapped to the inside, A1 gets mapped to the inside of B1, and the outside of A2 gets mapped to the inside of B2. And right, if you, so in particular, that yellow area over there got mapped into this yellow area by lambda, into this yellow area, to that yellow area by mu. Yeah, and this is a picture from Indra's Pearls, which is a fantastic, very beautiful book by Caroline Series, David Wright, and David Munford, that has lots of pictures of Schottky groups. So if you zoom in on this little picture here, you get a picture like this, which is why it's called Indra's pearls. Anyway, so we're looking at the space of things like this. And I'll end there.